All right, excellent. Well, welcome to day 2 of the 2021 Yampa Basin Rendezvous and to our first annual student research presentation session. Student research and training and the promotion of early career scholarship are essential to the Yampa Basin Rendezvous, its relevance and its future. So thanks to all of our student presenters here this morning, whom you'll meet shortly if you're just joining us, and to all those here in attendance, welcome. My name is Nathan Stewart. I'm faculty at Colorado Mountain College, and on behalf of my colleague, Madison Muxworthy, she will be co-hosting with me this morning. We all welcome you. So a few very brief notes here on in-meeting controls and session format, and then we are ready to kick off. So you, of course, arrived muted. Our presenters will unmute, of course, as they speak. That Zoom functionality feels really common for all of us right now. We really encourage you to use the chat. This is one of these silver linings, I think, in going virtual for sessions like this is, after a lightning talk, you'll see the format in a moment. The interactions between a presenter and the audience can continue. And so you'll see me here in written text encourage you as attendees to interact with our presenters, and then also our presenters to watch that chat, and your scholarly interactions can continue there. So we encourage that. This is a lightning talk format, which many of you are familiar with in concept, that sort of speed dating idea a bit of sharing sort of the meat of our findings. That's very much the format for today. So that 5 and 2 approach, 5 minutes for presentations, that's a screen share, 2 minutes for questions, move to the next speaker. You'll hear Maddie and I making those transitions and watching time for us. We have a proposed schedule of speakers. Thanks to all of you for falling into this order. We hope this works well still this morning. And we, with that, are ready to kick off. Martin, I'll stop screen sharing. Is it okay to have you take the floor? Maybe while you're setting up, I'd be happy to address any questions from the audience at all or speakers. We feeling pretty good? All right, excellent. I'm going to stop sharing here. Excellent, Martin. That looks like a great visual. Feel free to take the floor whenever you're ready.
Okay. Hi, everyone. My name is Martin. Over the summer, I worked on this project titled Avalanche Brutalities during atmospheric river events in the United States. My mentors were Kristen, Benjamin, Tamara, and Sasha. So just a little bit of background. In 2017, the first paper linking avalanche fatalities to atmospheric rivers was published, and there was a positive association between air frequencies and air-related avalanches, which makes sense since airs bring a lot of warm moisture, and warm moisture means a lot more snowfall and snowpack, which essentially leads to more avalanches. So the goal was mainly to identify which of these avalanche events were air-related, and the figure on the right is sort of like an example of what I was aiming to do. In terms of data, I used mainly avalanche reports of the United States. So this came from a bunch of websites, CIC, Yampa, Avalanche Center, and Precipitation. In terms of AR detection, I used the REPS AR catalog, which has a resolution of 0.65 longitude by 0.5 latitude. The methodology for determining AR-related avalanches was pretty simple. First, I would have like an AR detection algorithm to see if there was an atmospheric river near the avalanche event, both temporally and spatially. If this didn't work, I'll have to do a visual representation of the whole AR mask in an IVT plot to see if there was an AR around the region. And if that didn't work, it'll be an avalanche report reading of the weather that was happening during the avalanche event. So as you can see, this is a pretty long and long-winded step-by-step process. So the main goal that I was trying to do was seeing if the AR detection could be a little bit more robust, because that was the quickest way to determine if the avalanche was AR related or not. So this is an example. This is basically a map of all the avalanche events. There are over like 100 events from 2015 to 2021. So in terms of the AR detection region, these are some of the regions that I was playing with. As you can see, they sort of get bigger and bigger with each step. My goal was to try and see if there was any difference in terms of the size of this region. So like ideally, the biggest region would be able to collect the most number of AR related events. So after doing some sensitivity analysis, I kind of realized that there wasn't much change in terms of the number of the number of avalanche that was related to atmospheric rivers. As you can see, the number sort of stays the same even in the smallest sort of detection region, and it only kind of goes up by one when it gets like incredibly big. And the issue with it being incredibly big is that it might not be that accurate anymore, since the region that we're looking at is so huge, which is like almost the size of a state. The 2x4 is 2 degrees latitude by 2 degrees longitude by 4 degrees latitude. So essentially, it resembled sort of the shape of a rectangle. And these are also some of the total avalanche deaths in Western US and Alaska that were plotted throughout the years. So something that I was thinking of doing in future was to sort of look at composite shapes. So right now it's sort of looking like a rectangle, but I kind of thinking of making it look like an L shape or like sort of like a T shape. So that way it might be more efficient in terms of the algorithm. And then the other thing that I was thinking of doing was like a reanalysis of the 2017 paper, since we already know that the data, we already know which avalanches are AR related through that whole like 3-step process. So if I could somehow, I guess, improve the AR detection algorithm to spot more AR related avalanche events, that might also be helpful. The last thing that I noted was kind of interesting. There seem to be fewer AR fatalities during the higher precipitation water years. So like 2017, for example, has like only 10 avalanche deaths, but 2017 is a pretty high precipitation year for, at least for California. So, and I'm assuming the entire Western United States. So this is something pretty interesting. 2019 as well. It seems like somehow the AR fatalities are inversely proportional to the amount of precipitation during the water year. And that's all I have for this. Thank you.
Excellent, Martin, thank you. And right on time there in that 5-minute lightning talk, we greatly appreciate it. Let's open the floor here. We have a couple of minutes for questions. Would anyone like to kick us off here? Martin, I have a very first quick one, if it's okay to pose, and then maybe we could follow here. Do you feel like there's any pattern in that AR fatality note you just made is really interesting? Is there a particular pattern for warm years, do you think? Or I'm starting to think about the implications of rain on snow in the snowpack, and what is anything you could speak to there?
Not right now, because I think maybe the 2017 paper might be able to dig into that, because the other section, which I didn't have time to talk about, because I mean, was sort of like looking at the snow tile data of the AR related avalanches. So I'm assuming once we're done sort of deciding which avalanches are AR related, then that would be, like, we can gather more data through the snow tile. I was sort of thinking the fatalities would be like more like a psychological thing. I think because people kind of know like, oh, there is so much snowfall and this is so much rain, then they would be like, okay, let's maybe not do so much skiing this time. But in like 2016, when it was a dry year, people will probably just be going out to the mountains to ski, which would then lead to the fatalities. But that's more like a hypothesis.
Great, thank you, Martin. Other questions here? Feel free to mic in and pose a question, Martin.
Hi, Martin. I had a quick question. I think I might have missed it in your first slide, but what was did you have a cutoff size for the avalanches or just avalanches associated with fatalities?
Sorry, a cutoff slide?
I guess like a size or intensity of the avalanche.
Oh yeah. We were only looking at fatalities because only fatalities give like an avalanche report. So if like, it's kind of like if an avalanche happened and no one see it, like, did it really happen? So that's the main reason why we look at avalanche fatalities only. But I think in the future it would be cool to look at like all avalanches in general, because that would give, because right now we only have about 130 something cases. I think if we look at everything, there'll be like way more cases. we only looked at fatalities for this study.
Excellent. Thank you, Martin. And please continue that conversation with Martin in the chat. We encourage you to do so. And I'll transition us here to our next speaker, Lauren Bulletin. Again, thanks, Martin, for kicking us off. Lauren, take the floor when you're ready.
All right, will do. So for those who don't know me, my name is Lauren Bulletin, and I'm presenting my CW3E summer internship project investigating relationships between extreme hourly and sub-hourly precipitation in California, which I worked on with Drs. Nina Oakley and Luke Odell. Our motivation for this project came from the fact that post-fire debris flows and flash floods are hazards of growing concern in California, especially as wildfire activity and intense precipitation become more common with climate change, and we're at the greatest risk of these hazards when we get intense precipitation over burned watersheds within 1 to 2 years after wildfire. And while we have an abundance of hourly precipitation observations we can use to determine rainfall thresholds that can trigger debris flows and monitor when we're approaching those thresholds, we have much less availability of sub-hourly observations, which is why we wanted to know whether hourly precipitation data sufficiently represents the dynamics that are occurring at the sub-hourly scale. And so to do that, we started by looking at how precipitation is distributed temporally throughout rain hours. And we found that the continuity of extreme hourly precipitation varies spatially in California. And what I mean by continuity is when you have an hour of rainfall, you might have rain during just 1, 2, or 3 15-minute intervals or throughout the entire hour. And when we looked at extreme rain hours across all of our sites, we found that for the most part, there's rain occurring throughout the entire hour and less often during just 1, 2, or 3 15-minute intervals. But this does have a bit of spatial variation across California. So in Southern California in particular, we really see those cases where extreme rain hours have rain occurring throughout the entire time. And we still see that in Northern California, but we also see a greater representation of extreme rain hours where it just rained during part of the hour. And this has implications for how we interpret the intensity of rainfall. So where extreme hourly rainfall is less continuous, hourly rainfall intensities may underestimate the actual maximum rainfall intensity that occurs within an hour. So what I mean by that is when we have an hourly precipitation observation, we have to assume that that means the rain was distributed evenly throughout the hour, but that's, as we just saw, that's not always true. And so in this plot, I'm showing you for extreme rain hours again, what proportion of the total amount of rain that fell in the hour was contributed by the maximum 15-minute interval within that hour. And this plot is showing some cases where all of the rain in an extreme rain hour fell during just 1 or 2 15-minute intervals, meaning that the maximum precipitation intensity was actually much higher than the hourly observation would lead us to believe. And so now to actually look at the relationship between the two, I'm showing you hourly extreme precipitation on the x-axis versus the corresponding maximum 15-minute precipitation from those hours on the y-axis. And although the r-squared value isn't particularly strong, we see this relationship where, for the most part, these points are falling above the line that represents the threshold for intense 15-minute rainfall, meaning that hourly extreme rainfall generally contains at least one interval of extreme 15-minute rainfall. But what I'm showing you now is another plot using the same data from the same site, but we're approaching it from a bit of a different angle. So now I'm showing you extreme 15-minute precipitation on the x-axis versus the corresponding hourly rainfall for the hours that that rain fell during. And this threshold line now represents extreme hourly rainfall. And what I'm trying to show you is that extreme 15-minute rainfall may not always be recognized during hourly rainfall. So we have all these points that are falling below the line that represents extreme hourly rainfall. So if we only had hourly observations, we might not know that these extreme 15-minute intervals were occurring. And these extreme 15-minute periods may or may not be passing thresholds that can trigger debris flows. So in conclusion, hourly and 15-minute extreme precipitation are moderately positively correlated, but nevertheless, 15-minute precipitation observations are a very valuable asset for researching geohazards. And something that we're still hoping to understand is what drives the spatial variability between the relationships between extreme hourly and 15-minute precipitation in California, and whether those relationships are changing with a changing climate. I'm excited to hear your questions or what you think this would look like in Colorado. And you can also contact me at my email address, which is listed here.
Excellent. Thank you, Lauren. Great talk there. And let's open our sort of 2-minute Q&A here for Lauren. Anyone wanting to kick us off?
I have a question. Hey, Lauren, nice presentation. Could you go back to your second to last slide, scatter plot? You had 2 panels or something. The vertical axis there on the left panel is the max 15-minute rainfall. So if you multiplied that by 4, wouldn't that be the equivalent hourly rainfall?
Not necessarily. So in this.
No, I mean that basically you have a rain rate per hour rain rate. If you had 15, like that 0.5, if it kept raining at 0.5 for the whole hour, it'd be 2 inches per hour, right?
Correct.
So I'm just saying, somehow if you did that, it would just show how, and then you could divide by the hourly rainfall on the bottom and you'd have a percentile. Like if the hourly rain rate is 1 inch per hour, what are the odds that, you know, you've got double that rain rate, hourly rain rate, but only in 15 minutes? You see what I mean?
Mm-hmm. Yeah.
More just a suggestion.
Yeah, it'd be an interesting way to look at it. What I was just going to say is in this other plot that I showed, that's sort of similar to how I was originally framing this. So at first I made this plot, but I was showing what fraction the maximum 15-minute rainfall was, or what was it? I was showing what the hourly precipitation rate was as a fraction of the maximum 15-minute precipitation rate times 4. So like if you did have the maximum 15-minute precipitation rate occurring throughout the whole hour, I was seeing like, does that surpass the actual hourly precipitation rate or not?
Yeah.
I thought this was a little easier to interpret, but I see what you're saying about how you could get like a percentile from that. That would be interesting to look at.
No, I appreciate this graph as well. And I saw Mike Dettinger had a good question for you in chat.
And I'm happy to read that one out for everyone. Mike Dettinger says, what would the seasonalities of this look like in Colorado or California?
Yeah, I'm not super familiar with what goes on in Colorado. This is kind of like my first experience working with precipitation data, but at least in California, I think obviously certain places that are subject to like summer convective thunderstorms, you would see something different in that part of the year than in other parts of the year where like an atmospheric river could come in the cool season. So yeah, we didn't break it down by season, but it would be interesting to see how it changes throughout the year.
Excellent. Thank you, Lauren. I encourage folks to continue to pose questions to Lauren over there in the chat. Great discussion here. We're ready to move on to our third speaker. Rachel, feel free to share screen. And maybe as you're getting set up here, Lauren, I'll have you sort of look to the chat there. I'm going to drop a quick question in as well too. Great discussion there. Rachel, you're free to take it away when you are set up.
Awesome. Great job, everyone, so far. And thanks for having me here today. Awesome summer project here. My name is Rachel Santee, and this summer I was an intern with the Center for Western Weather and Water Extremes, Yampa Valley Sustainability Council, and a student here at Colorado Mountain College. I was able to work on a project in Steamboat Springs, Colorado, involving the beginning stages of implementation of a soil moisture monitoring network here in the Yampa Basin to better conserve and manage water in the midst of a severe westerly drought. My mentors were Anna Wilson, Madison Muxworthy, Nathan Stewart, Michelle Stewart, and Nicole Pepper. And here's a map of the Yampa River where this project took place, specifically here with the yellow star. Water in the West has become a huge issue, and the status of soil moisture in watersheds largely dictates what portion of rainfall or snowmelt contributes to stream flow or groundwater recharge. Which led me to my research question: how do in situ soil moisture measurements vary at a sub-basin scale, and what landscape level parameters potentially influence that variability? To the left is a map of the upper Yampa River Basin, outlined in gray. Circled in red is my first site location, the Buffalo Pass Wilderness, where I took 3 soil moisture transects in between SNOTEL sites labeled A and B. Circled in purple is my second site location in the Flat Tops Wilderness, where I took 3 soil moisture transects located near Snowtail sites labeled C. Another part of my site selection was kind of in-field observations of catchment areas, kind of just defined with a bowl in the landscape or stream location or ephemeral streams. To the right is an image of my transect line at each site, starting my transect in a catchment area to signify a water producing zone. Going upslope away from the catchment, measuring volumetric water content at 8 and 4.8 inches at 10 feet intervals until 100 feet or 150 feet. The purple box represents the TDR 150 soil moisture meter that I used for this project, which measures percent volumetric water content. These two graphs show the same comparison of in situ observations of volumetric water content along the y-axis and distance along the transect line, going away from the catchment zone upslope along the x-axis. In blue, we have volumetric water content at 4.8. Oh no. Hold on 1 second, sorry. Oh no. Sorry about that. The start of the transect line is in the catchment zone here. And as you move away from the catchment zone, volumetric water content decreases as you go into the grasses and shrubland. And then again, increases as you go into the tree canopy. And then again here, we started the transect in the catchment zone, showing a higher volumetric water content. And as you move away from the catchment zone, volumetric water content decreases, again in the grasses and shrubland, and then increases again as you enter the tree canopy. And so we kind of just defined a tree canopy as an overhead shade source. Oh, sorry, a little messed up here. The vegetation exposed is evapotranspiring at a much faster rate, losing water at a faster rate. Results are showing that there's a notable relationship between vegetation and water availability. That would be a very beneficial piece of data for water managers to use in our valley. Now I want to bring your attention to soil moisture and precipitation. Precipitation falls from the sky and interacts with the soil, where water is often lost or stored. Listed to the left is average volumetric water content from 3 sites at 2 different depths. To the right is precipitation data from in red Buffalo Pass and in blue Flat Tops, and the stars indicate which days I was at each site. The data shows an opposite correlation between volumetric water content in the soil and precipitation, measured in the Snowtail precipitation gauges. Kind of just showing that these graphs suggest that the Flat Tops, there's a higher volumetric water content, but a lower precipitation. Some conclusions from this research was in situ soil moisture measurements vary across a sub-basin. In situ soil moisture variability is influenced by landscape level parameters such as vegetation cover, soil type, aspect, and elevation. Sorry about the lights going off. And then I'm now open to questions.
Excellent. Thank you, Rachel. That's great. Maybe we could leave your slides up here in the case questions point us back to a given projection. Folks, let's open the floor here. Any questions here for Rachel right out of the gate?
I have a question, if that's cool. Why were 4.8 inches and 8-inch depths used for the volumetric water content? Just out of curiosity.
That's a great question. I think the soil moisture meter that we used kind of had a bunch of options, and that's kind of just what we chose. I don't know if I had, I didn't choose that, so not sure, but hopefully it represented enough. And I will say that I got a good amount of data, but not necessarily a lot. So Tim, do you have a question?
Yeah, Rachel, I'm curious, you mentioned in your summary that aspect could make a big difference. I'm wondering, and you didn't have a lot of sample size, but was there a difference in aspect between the 2 sites that might explain that negative correlation between precipitation and soil moisture? I'm just curious.
Definitely. Yeah, we tried to, Maddie was my field assistant for most of this project. Thank you, Maddie. And we tried to keep it pretty consistent between, I don't know about these ones specifically. I could definitely get back to you on that, but the first two measurements I took at each site were the same, and then the third one at each site were the same. And I think it was west for one of them. And yeah, sorry, I'm not fresh in my mind.
Yeah, I would, we should talk some more about that because I've been thinking a little bit about that in terms of thinking about, are there places we should be trying to hold moisture on the landscape, and weather aspect matters quite a bit in that discussion. So thanks.
Yeah, I definitely think it does. So I can look into it.
Right.
Folks, we're doing good on time here. Elise, do you want to mic in and share your question?
Sure. Hi, Rachel. So thinking about the different ways that soil moisture data can be collected, such as satellite or other non-on-the-ground measurements, what did you see were the specific benefits to doing on-the-ground work like this, or what were insights you thought you gained?
I would definitely say field observations, like being there on the land, being able to have a whole area to kind of explore and kind of identify those catchments was a huge benefit to it, instead of kind of just having like picking a random spot through satellite, I guess. It's totally different on the ground, in my opinion. And I think satellites definitely help you kind of choose where you want to go, but being able to see those water pathways on hand is super important.
Excellent. Thank you, Rachel. And thanks to all those posing questions here. Feel free, anyone here, to continue that conversation with Rachel and also Martin. Lauren, of course, has stepped off to go TA here, but those two, Martin and Rachel, are still with us. Hilary, I think we're ready to have you step up to the podium. Feel free to take the floor whenever you're ready.
Alrighty. Hello, everyone. I am Hilary Beckmeyer, for those that don't know me. I did my research on attributing commercial shipping losses to extreme weather in the North Pacific with Forrest Cannon, Ali Cobb, and Tom Quarringham. So motivation and data, marine shipping damages are approximately $107 million per year, and those are through insurance claims. Environmental impacts also, like dangerous shipping containers that fall in that have, like batteries and whatnot, can, create natural disasters or oil spills from like oil vessels. So the question is, do ARs contribute to these damages? The data that we used was Lloyd's of London as an insurance company, and they gave us some information on different vessels that were damaged. And then also through news articles, we found ones that were of like particular interest. And then I used ECMWF's reanalysis ERA 5 data. And the main incident that I looked at was the Meritus Pelhambang, which is from I had an accident on the 4th of January in 2011. But there were also 5 other case studies that I looked at afterwards just to find continuity through that. And in order to look at these, I calculate and assess them properly. I calculated IVT. And then, as you can see, where I didn't actually use the integral, I used from the ECMWF ERA 5 data, the vertical integral of eastward water vapor flux and the vertical integral of northward water vapor flux to find it overall. So, and then other variables considered were maximum individual wave height, total precip, pressure, and wave period. Resolution was 1/2 degree latitude and longitude for the ocean and 1/4 degree for the atmosphere, and temporally it was hourly. So these are just some of the images that you can see. On the way left is 2 days before the incident, the mean over the course of the day, and then in the center is the day before the incident, and then to the right is the day of the incident. So as you can see, there was an AR, and you can see below the precip. And then there's also the scalar pressure as well, and hectopascals as contours. So you can see that was actually relevant in it. And then I also looked at the other variables, as I mentioned. And as you can see, the 24 to 48 hour span is the day of the incident, and then 0 to 24 is the day before. So in every single one of these variables that I looked at, you can see that it increases as it goes into the day of the incident. So it definitely shows that there is correlation to some degree. And these are all the different case studies I looked at. The Hawaiian Patriots in red, that's the one that actually was not, did not have to do with an AR. It was probably just, but it was also quite equatorially located. And then you can see the Meredith Pelemang, it actually had uranium that leaked. So another natural negative instance that could occur. But yeah, so those are all the ones that I looked at, and all of them except for the Hawaiian Patriot and APL China were caused by, or were not caused by, but were associated with ARs. So conclusions: ARs associated with container ship accidents when inclement weather has been noted to be the cause. Precipitation is definitely a factor in the storms as well. And IVT, max individual wave height, total precip, all of the variables that I looked at all increased on the day of the accident. So there's a ton of future work that I've looked into, considered looking into more. There's so many different directions you go with this. And to the right, there are just some books that are very interesting about shipping container accidents due to storms and just how they're impacted. And they're actually really fun to read as well as super interesting. So, and thank you to Allie, Tom, Forrest, Cody, Will, Mike, Anna, Douglas, and just CW3E for the opportunity to do this research.
Excellent. Thank you, Hilary. Great talk there. Let's open our 2-minute Q&A for Hilary. Any questions from the group? Hilary, I had a really quick first one that you might be able to speak to, and this is sort of like research findings application potential zone. I know we, of course, can use ship tracking, common ship tracking for, say, the merchant marine fleet to understand where ships are from various flags of origin, and that fleet is really highly variable, right? And it's like seaworthiness, those vessels. Do you see some potential to watch ARs sensitive to the vessel by type and the sea they're in to give an early risk warning? Is that one of the obvious applications here?
So yeah, it's just this finding, being able to do more of an earlier warning will then hopefully diminish the amount of accidents and incidents that cause it. So if our applications for predicting ARs improve, then we can, not have uranium leak into the ocean and all of those unfun things. So yeah. Anna, you have a question?
Yeah, hi. Thanks for that great talk about your work, Hilary. That was awesome. I guess I wonder, what do you see as potential, so for example, ARs can be super enormous, right? And cover a ton of area. Is there any future to looking at what sort of sectors of the ARs are associated with these dangers? Or could you look at that with the case studies you've already done, just to say to be able to sort of geographically restrict maybe a warning area of the?
Actually, one of the things that we've noted is that, let's see if I can just, is that it actually happens to be on the lower right or side in a lot of the incidents that I looked at. And so one of the things that I was discussing with future work is doing ship-centered composites. So in relation to the ARs, to actually see if that's consistent across different instances, because that would be extremely beneficial. So yeah.
Great, thanks.
We're doing great on time here. Other follow-up questions here for Hilary? Excellent. Hilary, thank you. And again, audience, feel free to continue to interact with Hilary and prior speakers over there in the chat. Excellent. I think we're ready to transition here to our final student presenter. Erica, you're welcome to take the floor when you're ready and share screen. Do let me know if I can provide any assistance at all, and no rush, we're doing great for time. So take your time sharing over. Awesome, Erica. You've got a solid visual. Feel free to take the floor.
Hello, everyone. Thank you for having me today. Let me just move this out of the way. Okay, yeah, so my name is Erica Shivers, and I was an intern this summer at CW3E, and I studied the impacts of atmospheric rivers on extreme snow events in the White Yampa River Basin. And my mentors were Zen Zhang and Julie Kalansky. And just a brief overview of why it is important to study the climatology of extreme snow and its relations to atmospheric rivers is because over half of the normalized stream flow in Colorado River originates from water released by snowmelt. So therefore, it's significant to understand how atmospheric rivers can affect the snowpacks in the basin. So in addition, ARs typically yields a large amount of snow accumulation when they make landfall during cold seasons. So in this study, we examine the impacts of atmospheric rivers on extreme snow events in the White Yampa River Basin. Okay, so I'll go right into my results for the purpose of this presentation. So average over 21 stations in the White Yampa River Basin, the mean annual maximum sweep. Oh, actually, let me just describe this graph. So it's basically the annual maximum sweep for the White Yampa River Basin from the years 1990 to 2020. So 30 years. And then the average over the 21 stations in the White Yampa River Basin, the mean annual maximum sweep is about 28 inches. And the standard deviation is about 4.96 inches in the 31 years, as you can see in this figure. So just to note, we did not find any statistically significant trends for the annual maximum sweep in the 31 years of the White Yampa River Basin. However, there are large interannual variabilities. For example, in the water year 2011, it had annual variabilities. It had, I was nearly 37 inches of sweep. So, but in the next year, in 2012, it only had about 15 inches of sweep. So that was about 40% of the 2011 sweep. These changes could have like large impacts on the California water supply. And the extreme sweep events throughout the 21 stations deliver about 5% to 6.5% of total sweep a year in the White Yampa River Basin, as you can see in this figure. And this also plays an important role in the interannual variability of the annual maximum sweep. So next, I want to show you the 99 percentile sweep threshold. And as you can see here, Tower has one of the biggest thresholds, and I marked that by the size of the square. And Battle Martin has a very small threshold. So this is just like a brief overview of just how each station and has their and the information on their threshold. So I will go to the next slide, and just to give you an example of what this is a this is an extreme snow day associated with an AR, and I took this from January 11th, 2017. So what we are interested in are the impacts of ARs on extreme snow events in the White Yampa River Basin. So we examined the IVT field as well as the detected AR conditions on those extreme snow days. So if there was a detected AR covering any part of this blue box on the right, basically within those coordinates on that extreme snow day, I defined it as an extreme snow day associated with an AR. So the blue box is larger than the white Yampa River Basin. That's primarily because atmospheric rivers within that blue box may have a great impact on the snow in the white Yampa River Basin, although the AR does not directly hit the basin. So I found that out of the 37 extreme days I found for the 99th percentile, 12 days, approximately 32% were associated with ARs. Okay, yeah, so those are my results. And some things that I would like to discuss is the future work. So atmospheric rivers have large impacts on extreme snow events in the White Yampa River basins, as we can see from the results presented. So more research is needed to deepen our understanding of the impacts. For example, if we use the 99th percentile, the 95th percentile instead of for the SWE thresholds for selecting extreme snow days in 1990, 2020, we can use those instead of the 99th percentile. And we can also examine the AR catalog for 1 to 3 days before the extreme snow days. And we can also examine the AR characteristics related to extreme snow events. And that's it. Thank you.
Excellent. Thank you, Erica. Great talk. Let's open up here our Q&A for Erica. This is, of course, our final Q&A here before our transition over to our main sessions. Questions for Erica?
I have one if no one else does. I didn't want to jump in since I've asked some questions already. So Erica, I noticed on the graph that you shared, your second slide, it seemed like the difference between average snowfall and the snowfall with an extreme weather event was actually a pretty similar amount across most of the sites. And I was curious if you had any thoughts to share about that.
Okay, so your question was the amount of extreme snow, or what? I'm sorry, what was the question?
So the orange bars, essentially, if I'm reading it correctly, and please tell me if I'm not, all seem to be between roughly 5 and 6 inches of SWE, which to me seemed like a pretty similar amount across the sites, as opposed to one site, say, having a difference of 10 from the extreme event and another one only having a difference of 1. And I was curious if you had any comments about that.
Not particular. The data was pretty much consistent throughout. I also did the same graph for the 95th percentile. So they all range between 5.02 all the way up to about, I would say, 676. So that means that they're pretty much consistent throughout the basin. And there isn't any significant difference when it came to extreme weather for the Yampa River Basin. But as you can see, for the non-extreme SWE per water year, Tower exceeded above all other stations. I hope that answers your question.
We could steal, thank you, Erica, and great question, Elise.
No problem.
I think we could steal a moment to sneak in a final question if there's one out there. I don't want to cut anyone off who might
I
be
think,
waiting to ask. Yeah.
I think Tim's has a question.
Yeah, I don't know if Marty is still on as well, but I'm just curious between Erica and Marty. Marty made a presentation yesterday that showed how influential the extreme events were on the accumulation of snowpack, but these results that Erica's showing doesn't show that the extreme events are actually that significant in terms of total SWE. Am I missing something to reconcile those two findings?
Well, I only took the 99th percentile. Like, that's why I wanted to emphasize on the future work, because there's so much more to be done. And I did this research and analysis in only 5 weeks. I'm sure Marty has been working on this for years. So there's so much more research to look into. I've only taken the 99th percentile. Like I said, I can also do the 95th percentile, and I'm sure there will be, it will probably be a lot more significant if I had more time to do more research, because these results are very minimal. I just want to stress that.
Okay, well, that's helpful. They're really interesting though to think about. So thank you for beginning to do this analysis. Yeah.
Excellent. Thank you, Tim. And thank you, Erica, for that response as well, too. Well, folks, I'm watching time here in our sort of broader schedule for the day. And just wanted to be the first to thank all of you, our student presenters this morning, Martin, Lauren, Rachel, Hilary, and Erica. Really excellent work. Stellar research undertaken and presented here. You are a remarkable first group of student presenters at Yampa Basin Rendezvous, and you've established a bar we really hope to maintain. So thank you again for your work. I'll invite all of us here to transition over to our main Zoom link for our first panel session of the day. And just to remind you, this is Current Management Water Strategies. We hope to see you all transitioning over there in just a couple of minutes. Thank you again to all of today's speakers.